Welcome to PH 101 lab. I'm Ahmed Ali, and our today's experiment, that is our second experiment, is about translational equilibrium. So in order to proceed, we must discuss the prerequisites which we will need for this experiment. That is the requirement for this experiment that we will perform shortly. So what are the prerequisites for this experiment? The first one is vectors, and the second one is the addition of vectors. So we must be aware of these two things. So what are vectors? Actually, vectors are physical quantities. So any quantity that we can measure is actually of a physical quantity. So the physical quantity having both magnitude as well as direction. So we will say that quantity is known to be a vector quantity. I can give you a very simple example. Let's say if 50 Newton force is acting along x-axis on a body of mass m, so we can say that it is a vector quantity. Force is a vector quantity. Here we can explain it very simply. Let's say this is a block of mass m and it is placed along x-axis, and a 50 Newton force is acting on this block of mass m in this direction. So actually force, the magnitude of the force is 50 Newton and it is acting along the x-axis. So it has both the magnitude as well as a direction. So this is actually a vector quantity. So there are many vector quantities: velocity, displacement, acceleration. So there are many vector quantities. So the vector quantity has both magnitude as well as direction. So unlike scalars, vectors have both magnitude as well as direction. So it is very simple. So the second one is the addition of vectors. So just like we add ordinary addition, 2 plus 5 is equal to 5 plus 2. So we cannot add vectors like this, because vector has not only a magnitude, they also have a direction. So we cannot direction like this. So there are two methods. One is the graphical method and the other one is the mathematical method. So this method, we will discuss mathematical method shortly in our theory and calculations part. So we will discuss this one later, the mathematical method. First we will discuss the graphical method. So what is actually the graphical method for adding vectors? So graphically we represent a vector by an arrow, simple, by an arrow. So this is actually representing a vector quantity. The starting point of this arrow is actually the tail. We call this initial point the tail. That is the starting point of a vector quantity, and this is known as the head. So this is the ending point. So it shows the direction of a vector quantity, in which direction the force is acting. The velocity of a body, the body is moving in this direction, so it can represent a velocity, it can represent a force, and the length of the vector determines the magnitude. So if the length is more, it has a larger magnitude, it has more magnitude, and if it is smaller, so it represents a smaller magnitude. So let's say this is F is equal to 100 Newton. So this is the length of the vector determines the magnitude, and the arrowhead determines the direction in which direction this force is acting. So actually this is the representation of a vector quantity. Every vector quantity is represented by an arrow. It must have a head and a tail. So this is the starting point, and we can say this is the ending point, the head. So how to add vectors graphically? So this is the representation of a vector graphically, and how to add them graphically? So we must know about the head to tail rule. So there is a rule known as head to tail rule. So head to tail rule is used to add or subtract vectors. How to use head to tail rule? So let's say I will give you a very simple example how to use the graphical method to add vectors. So let's say this is F1, it is a vector quantity, and let's say this is F1, it is acting along, or it is acting in this direction, simple. And there is another force that is acting in this direction, F2, and we have to add these two So we should represent a vector. A vector, let's say, is generally represented by any letter, capital or small, with an arrowhead above, or you can represent it with a bold letter like this. The arrowhead can be above, the arrowhead can be below. So you can use any of the notation. Better to use either this one or this one with an arrowhead above. This is the simple representation. Symbolically, a vector is represented with an arrowhead above. So this is actually representing a force with an arrowhead that represents the direction. So how to add these two vectors? Simple. This is the head of the first vector. Head of first vector. And this is the tail of the second vector. So how to add them? We will put the tail of the second vector on the head of the first vector, and we will keep the vector as it is. We will not disturb its direction, we will not disturb its orientation. So we will take this vector and we will put it here. The tail of the second vector will be placed on the head of the first vector. So we will put this vector here, and the direction will be upwards. We will not disturb its direction. So this is the way how to use it. We are using head to tail rule. So we are placing the tail of the second vector on the head of the first vector. Now the resultant will be actually this one. The initial vector, the starting point of the first vector, and the ending point of the second vector. So we will draw a vector here. So this is actually the resultant of these two vectors. Means the addition of two vectors gives a resultant vector. So this is actually representing the vector sum of these two vectors. This is the resultant vector. And how to know whether this one is the resultant vector, or this one is the resultant vector, or this one is the resultant vector? So if we see, the head of the resultant vector coincides with the head of the second vector, and the tail of the resultant vector is coinciding with the tail of the first vector. So this is actually the property of a resultant vector: head and tail. So this is representing the resultant vector. So actually this is the way how to represent vectors graphically. So we will be using a proper scale for them, but this is just a simple example to add the vectors graphically. We will be discussing mathematical method in our theory and calculations part. So the next thing is, this was all about the prerequisites. Now we will discuss the translational equilibrium shortly. So this experiment is about translational equilibrium. First we should know what is equilibrium. So equilibrium is actually a state. Simple, equilibrium is actually a state of a body. Halat, body किस हालत में है? So this is representing a state. This is not a physical quantity, it has no unit. So translational equilibrium is if the vector sum of all the forces, so vector sum means if we are using this method, so we will add vectors graphically, and if we are using mathematical method that we will be discussing shortly, so the vector sum of all the forces must be equal to 0. So what does it mean? So if the force is 0, from Newton's second law we know that F is equal to mass into acceleration. So if mass is constant, which is constant, F is directly proportional to acceleration. So if force is 0, then the acceleration must be equal to 0. So the net sum of all the forces acting on a body is equal to 0. It means that the acceleration of the body is equal to 0. And acceleration is 0 in two cases. Either the velocity of the body is constant, or the velocity is equal to 0. So if the velocity is constant, there is no change in the velocity, then the acceleration will be equal to 0. And the vector sum of all the forces, if the vector sum of all the forces acting on a body is equal to 0, then the acceleration in that system is equal to 0, and we can say that the system is at rest or moving with constant velocity. So we will not be discussing this one, the case when the velocity is constant, means the body is moving with constant velocity. So we will not be discussing this case. We will be discussing when the velocity is equal to 0, when the body is at rest. We will be discussing just this one. So in this case, if the velocity is equal to 0, the acceleration is equal to 0, and it means the vector sum of all the forces acting on a body is equal to 0, then the body is said to be in translational equilibrium. And translational equilibrium means that the center of mass of the body is at rest. Simple. The center of mass of a body is at rest. So let's say this is actually, let me give you a very simple example. Let's say this is a body of mass m. So there are certain forces acting on this body. Let's say this is F1 force acting on this block of mass m in this direction, and this is F2 acting on this block of mass m in this direction. Now how to add these two vectors? The summation of these two vectors using proper rule, graphical method or mathematical method, head to tail rule, will give us, if I place this vector here, then the resultant will be here. So this is actually the resultant of these two forces, Fr in the subscript Fr. Now if there is another vector that balances the resultant vector, then the vector sum of all the forces acting on the body is equal to 0, will be equal to 0. So how to balance this Fr? If I draw an equal and opposite force in this direction. So this is let's say I draw a force in the opposite direction to the resultant force that must be equal in magnitude to Fr, which means that Fr is equal to, let's say I call this force is Fe, equilibrium force, that we will be discussing shortly. What is equilibrium force? So if Fr is equal in magnitude to Fe and both are in opposite direction, so I will represent it with a minus sign. Fr is pointing in this direction, Fe is pointing in this direction, or both the forces are pointing, or they are anti-parallel, having the same magnitudes, or they are at 180 degrees to each other. So this is now the vector sum of all these forces. The resultant of these two forces is this one, and this is balanced by the equilibrium force. So it means that this system is at rest, it is not moving. So we can say that the velocity is equal to 0, means it is at rest. The velocity of the center of mass of this system, let's say this is the center of mass of this system, so the velocity is equal to 0. It means that this block of mass m is at rest, which means that the acceleration is equal to 0. And when it is at rest, if I add these all vectors, I will get, if I add all these vectors, I will get a 0. I will get a 0. So it means that if the vector sum of all these forces acting on this block of mass m is equal to 0, then I can say simply that this block of mass m is in translational equilibrium. So this, I think this is enough for the prerequisites, and after the prerequisites we will be discussing the apparatus that will be required for our experiment, and then we will proceed. Now the apparatus required for our experiment is what we will be using in our experiment. The first one is the force table that as you can see, we need 3 pulleys that are adjustable. We must have masses. We have mass hangers, we have strings, we should have a metric rule, protractor, white sheets, and also we will need a graph paper to plot the vectors graphically. So this is the apparatus required for our, so this is actually the apparatus required for our experiment. So as we perform experiment, we should be aware of the objective of the experiment. So what is the objective of this experiment? To determine the resultant of two forces and also the equilibrium force that balances the resultant force. So we discussed that the equilibrium force is a force that balances a resultant force, and that is equal in magnitude to the resultant force, and it is always in opposite direction or anti-parallel to the resultant force. So we will be determining the forces when the system is in translational equilibrium. And how do we know that the system is in translational equilibrium? We will be using the force table. So there will be certain forces, and in order to balance those forces, there will be a ring, and we will be using that ring to place it exactly at the center of the force table. So when it will be exactly at the anchor point at the center, that we will be demonstrating in our experimental part. So we will later we will later discuss how to balance the forces using the force table. So this is the apparatus needed. We will determine the resultant of the two forces, and then we will the resultant of the two forces will be balanced by the equilibrium force. So actually there are three methods to perform this experiment. The first one is the experimental method, the second one is the graphical method, and the third one is the mathematical method. So the experimental method is by looking into the force table. What are the forces? There will be a degree scale that I will be demonstrating. The degree scale will give you the direction. The F1 is, let's say, at 0 degrees. So we will be using the experimental method, and the theta r will be determined for the equilibrium force. Then from the equilibrium force, first we will determine the magnitude of the equilibrium force. We have two forces, F1, F2, and these two forces will be balanced by the equilibrium force, and definitely the equilibrium force will balance actually the resultant of those two forces that we will be finding, that we will be determining. So first we will determine experimentally the equilibrium force. What is the magnitude of the equilibrium force, and what is the direction by looking onto the force table. We can easily experimentally say the direction and the magnitude. If we know the resultant vector experimentally, then we know that if this is the magnitude of the equilibrium force, then the resultant force must have the same magnitude as the equilibrium force. And if the resultant force has a direction theta e, then the direction of the resultant force will be in opposite to the direction of the equilibrium force. So these two forces are always equal in magnitude. So if you have the equilibrium force, you can easily find out the resultant force simply experimentally as well as mathematically. Graphically, how we will add the vectors? Then we will be using a graph with a suitable scale. It depends on the forces that we will calculate, F1, F2. So when we calculate the forces, then we will use a suitable scale accordingly, and then we will plot these vectors on our graph paper, and then we will draw its resultant, and we will verify a parallelogram law of addition. So we will later come on to the parallelogram law of addition or commutative law of addition. Then we will be adding vectors mathematically. How to add vectors mathematically? One way was the experimental, one is the graphical method that we discussed, and the other one is the mathematical method. So this is a rough sketch of a force table that is resting on a table surface. It should rest on a table surface. So this is the force table. This is just a rough sketch to understand. This is pulley 1. This is our pulley 1. This is our second pulley. These are adjustable pulleys. So we can move these pulleys up and down, as well as we can move them, we can rotate these pulleys accordingly to make this plastic ring exactly at the center. So if this plastic ring is not exactly at the center, then this system is not in equilibrium. So we will have to keep this exactly at this center. So these are the strings, and this is the first force, F1. This is the mass hanger, and these are the masses. So this is the first force, this is the second force. The resultant of these two forces is actually here, Fr. So it means that this F1 and F2 force is balanced by this third pulley. This is the equilibrium pulley, or you can say that we can adjust this one. So first we will make an initial setup. We will make our force table. We will be using strings that will pass over the pulley, and then we will attach them with the mass hangers accordingly. This is the first force, this is the second force, and this is the equilibrium force. So this is the first mass we will put here, the second mass, and the third mass. So the masses may be equal or they may be different. So experimentally, if this is a degree scale, so f1 can be, we can easily say that let the f1 is at 0 degree. So the angle of f1 is at 0 degree. Let's say we say f2 is at 120 degree. So this is at 120 degree. Let's say we say that the equilibrium force is at 230 degrees. Let's say this is at 230 degrees. From looking onto the table, we can easily say experimentally that f1 is at 0 degrees, f2 is acting at 120 degrees, and f equilibrium is acting at 230 degrees. So if this is the equilibrium force, we know that its opposite force will be resultant force. So it means that if I subtract 180 degrees from 230 degrees, it will give f 50 degree. So this 50 degree is actually theta r. So experimentally we can determine the resultant force from the magnitude, from the direction of the equilibrium force, just simply by subtracting 180 degrees from the angle on the force table of the equilibrium force. So the equilibrium force is acting at 230 degrees. So if I subtract 180 degrees, I will get the resultant vector, because these two vectors are at 180 degrees. So I will get experimentally the direction of the FR. So this is now at 50 degrees. So this is the way how to this is the way how to resolve and how to set. This is the initial setup. Pulleys with mass hangers, and this is the center ring. These are the threads. So the threads actually provides a tension. So this tension is provided by these masses. So now we know that if these masses are hanged, so there must be a force because there is gravity. So these masses, we can call these masses as weights now. So these are weights actually, because if we know that weight is a force, so F is equal to mg. We will be using F is equal to ma. Instead of A, we will be using mg, and this mg is known as weight. Now this is weight 1, I can say this is weight 2, or this is force 1, and this is force 2, and this is the equilibrium force. The equilibrium force is balancing these two forces. Don't worry, we will be discussing this on in our experimental demonstration. You will understand it better. Keep in mind, we will adjust the pulley accordingly, and the pulleys must be on the same level, because we can adjust the pulley up and down, and we can also adjust that we can rotate the pulley on this force table as well. So there are adjustable screws that you can use to make the pulley a little up or a little down, or you can rotate this pulley on this table. So better to fix F1 and F2 and to adjust just the third pulley, the third one, that is our equilibrium force pulley. So better, for the sake of simplicity, you can start from anywhere. But if you will keep your force, the first pulley at 0 degree, and the second pulley can be placed either at 120 degree or 90 degree or 130 degree, it depends on you. So if I will be using this table, I will place the, for my simplicity, I will use F1 at 0 degree, and I will use F2 at 120 degree, and then accordingly, when I will fix these two pulleys, I will then accordingly use the equilibrium force pulley. So it should be at, it might be at 230 degree, or it might be at 210 degree, 210 degrees, it depends. How do we know that the system is in equilibrium? So if this plastic ring, there will be a plastic ring that is held by the strings, that is, this plastic ring is acting upon these three forces. So the plastic ring is acting upon by F1, F2 and equilibrium force. So there is a central point. So if this plastic ring is exactly at the center, you will have to bring it exactly at the center. Then you will perform your calculations. So if it is exactly at the anchor point, exactly at the center, then it means that the system is in translational equilibrium. Then you will perform, then you will proceed. This is the first step. Make the system in equilibrium. Check the pulleys, the level of the pulleys, all the pulleys are at, it should not be like that if this pulley is upward and this pulley is downward. So the forces will not act uniformly. So in order to make the forces horizontal, you have to keep the pulleys at the same level, not too much high and not too much low. So these must be at the same level. So, and the other point, important point is, this plastic ring should not touch the table, should not touch the central point. It should be a little above. It should not rest on the table. So this should be a ring. It should be a ring. It can also be a ring. So a ring will be tied from here. This force 1, this is force 2, and this is force 3. And there will be a central point. So you have, the ring should be at the center. It should be either a plastic ring, and it should be at the center, or it should be a ring. It can also be a ring. So it should be exactly at the center. If it is not at the center, let's say the central point is this, and if it is not at center, then we can say that it is not in equilibrium. So you will not perform your experiment if it is not at center. You should have very safe hands to perform this experiment. Now there is something that I want to discuss. We have not yet discussed the mathematical part. The mathematical part. So if this is F1, so the masses are hanged. We will place the masses in the mass hanger. And keep in mind, the mass of the hanger is also 5 grams. So if you are using masses, you have to add the mass with the mass of the hanger. Let's say you put 10 gram of mass here. Then the total mass with the mass of the hanger is 10 plus 5 grams will give 15 grams. So it includes the mass of the hanger for these 3 cases. For this case, for F1, the mass of the hanger should be included, for the second and for the third case. So what is the mathematical part? So there is gravitational force. So I can say that F1 is equal to m1g. This is the first force. And for the second force, F2 is equal to m2g. Now we will be given masses. Masses should be, we will have 3, we can perform different experiments. This is, let's say I call them P1, P2, P3. Experiment 1, you can call this task 1, task 2 and task 3. In the first task, let's say I keep the masses 15 grams and 15 grams. You can keep it at 10, 10, 5, 5, it depends on you. Let's say in the second case, I keep the masses to be 30 grams and 30 grams. So we will increase the masses. In the third case, we will put different masses. Let's say 15 gram, 20 gram, and let's say 25 gram. So we can change them accordingly. If you do not have these masses, 15 gram is not available, then you can use 5 grams. So these are 3 different experiments. We will have to repeat P1 experimentally, graphically and mathematical method. Similarly, for the second case, we will be using experimental, graphical and mathematical methods. Similarly, for the third case, we will be using experimental, graphical and mathematical method. So for these 3 cases, we will be using these 3 methods, and then the table should be filled accordingly. For the experimental method, for the graphical method and for the mathematical method. So resolve these vectors. It means that this is a vector quantity. It must have two forces acting on it. So this is acting along x-axis as well as y-axis. There are 2 components. So it means F1x is equal to F1 cos of theta 1. Let's say this angle is F1. For F1, I am using theta 1. For F2, the angle is, let's say, theta 2. Right? So this is F1 is equal to F1 cos theta 1. For x, we use the cos theta. And F1y will be F1 sine of theta 1. So this is for F1, the components. We have to find the components for the mathematical method. Now for F2, similarly, for F2 is equal to F2x is equal to F2 cos of theta 2. And F2y is equal to F2 sine of theta 2. Now we will add the corresponding components, the x components and the y components. So this will give Fx is equal to F1x plus F2x. Now we will add the y components of the two forces. So it will give Fy is equal to F1y plus F2y. Now we can easily find the magnitude of the resultant force. How much is the magnitude of the resultant force? The magnitude of the resultant force, the length of this vector. So it is equal to the sum of the square of these two vectors, fx and fy. So it is fx square plus fy square. This will give the resultant of this force. Now if you know the y component of the resultant force, the x component of the resultant force, then you can easily find the direction of the resultant force. You tan inverse fy by fx. So this will give you the direction of the resultant vector. So this is the mathematical method. You have to find the forces. You can also do it for the equilibriant force. You call it just, this is the equilibriant force, so you can say Fe is equal to MEG. So Me is the mass of the equilibriant. The mass you are using, I'm using Me, equilibriant mass, just for the sake of simplicity, and Fe for the equilibriant force. So it must have two components, Fex and Fey. You can also calculate the components of Fex will be Fe cos theta E. Cos theta E is the angle of the equilibriant force, and Fe sin theta E. This is the angle of the equilibriant force, the y component and the x component. Then there is no need when you find, because when you find, there is no need to do this. When you find the resultant theta r, then you can easily calculate theta E, the equilibriant force direction from this theta r. You can easily calculate. So this is the mathematical method. You have to perform these steps. Theta 1 you will get from here, and theta 2 you will get from here, right? And this is the, similarly you will put these values here. Keep in mind, if this is cos 120 degree, it will give you a negative sign. You have to include the negative sign in f1x. Then when you will be adding f1x with f2x, then you will be using that minus sign here. Let's say f1x is 0.5 Newton and f2x is minus 0.05, let's say minus 0.6 Newton. You will be subtracting them. F1x minus f2x is equal to 0.5 minus 0.6. It is because f2x can be negative, so you will have to include the sign. Keep in mind, if this is, let's say, cos 120, so cos is negative in the second quadrant, so it will give you a negative answer. It will give you a negative value. F1 you can calculate from here. Masses are given and G is 9.8 meter per second. Now keep in mind, you have to use SI or CGS. Either you convert this 9.8 meter per second square, convert this meter into centimeter. So it means 9.8 into 10 raised to the power 22 centimeter per second square. So the masses are in grams. The gravitational acceleration is now in centimeter per second square. The theta is in degree, and the forces are in Newton. So you use this notation CGS, or you can convert the masses into kilograms. You will convert this mass into kilogram if this is in gram. Divide this by 1000, you will get this in kilograms. You will get this in kilogram, and you will have to keep you will be using this value 9.8 meter per second square for SI system, and for CGS you will be using 9.8 into 10 raised to the power 2 centimeter per second square. So keep in mind, you will use the same set of units. Okay, so this was for the mathematical part. So now keep in mind, these pulleys are fractionless. We are considering that these pulleys are fractionless. We are not including the fractional forces. So keep in mind. Now what we will do, let me explain a little bit the equilibriant force. Let's say this is your F1, right? And this is your F2, right? and this is, let's say, your resultant force Fr. This is your resultant force. Now we know that there will be an equilibrium force exactly opposite to and equal in magnitude to this Fr. This is Fe, equilibrium force, that is balancing this resultant force. Now remember, conventionally we take angle, let's say this is our positive x-axis. This is our positive x-axis. We take our angle in the anti-clockwise direction with the positive x-axis. Conventionally, we can take it clockwise, but that will be considered negative. So conventionally, we take angle with the positive x-axis in the anti-clockwise direction. So this is actually the resultant angle direction, theta r. This is theta r. Now, what will be the direction of this equilibrium force? So actually, the direction of the equilibrium force will be determined from the positive x-axis, right? From the positive x-axis. Now look at this figure very carefully. It means that this is our theta E. Now this theta E is equal to, if I add this theta R with this, so this total is 180 degree. This from, because these two vectors are anti-parallel, so this total is 180 degree. So if I add 180 degrees with this theta R, then I will get this complete angle theta E, right? If I add this theta R with this 180 degree, so I will get this complete theta E. So this is the way how to find the direction of the equilibrium force. Just add 180 degrees with the resultant force. But keep in mind, this is for the case when the resultant force is in first, second, third quadrant. What if the equilibrium force is here? This is our equilibrium force, and let's say this is now our resultant force. Let's say, so now the case is different. We will not be using this one. This was just for this case. So this is Fr and this is Fe. This is Fe. Now, as I said, that we take the angle in the anti-clockwise direction, right? So this is our positive x-axis. This is our F1, let's say. This is our F2. And this is there, these two forces gives this resultant, and this is balanced by the equilibrium force, which is unfortunately now in the second quadrant. So what we will do, let's say this is, let's say, an angle, and this should be, we know that this is at positive, this is making an angle of theta E, which may be any angle. Let's say this is 140 degree. This is theta E. So how can I find theta E? This TFR is now negative. This is now negative. This is in the clockwise direction. So this is theta R. So it means that these two angles, this complete from here to here is 180 degree. 180 degree is this complete green semicircle. This is because these two forces are at 180 degree. So if I subtract theta R from this 180, it means that if I subtract this portion, if I subtract this theta R from this 180 degree, I will get this black arrow. Means if I subtract this theta R from this green semicircle, which is 180 degree, so 180 degree, so it means if I subtract 180 degree minus theta R, 180 minus this theta R, I will get this angle. So it is equal to now theta E. So it depends where is our equilibrium force. If it is in this quadrant, third quadrant, then you will be using this one. If it is in this quadrant, you will be using this one. If it is here, then you will be using different way. You will be calculating the angle, you will be determining the angle with the positive x-axis in the anti-clockwise direction. Keep in mind. So you should be aware of how to find the direction of the resultant force and how to find the direction of the equilibrium force. So this is very important. You should be aware of these things. So it means that if you know theta r, you can find theta e. Experimentally, if you know theta r, you can find theta e, and you can easily find the theta e from this force table. Let's say this is at 230 degrees mark. So this is your theta e. So if you will put theta e here, because now the resultant, the equilibrium force is in third quadrant, so I will be using this equation. So if I add 230 degree, let's say this is our equilibrium force, so theta e is 180 degree plus theta r. So if I'm if you want to find this fr, theta r can easily be found by theta r is equal to theta e minus 180 degrees. So theta e is your 230 degrees. That is why I was using this one, 230 degrees minus 180 degrees. It will give us 50 degree. So this is our direction of the, this is just, you have to play with the equation. This is simple. You just have to play with the equation. You have one value, you can find the other value. So this is very simple. So this was about the experiment number 2, translational equilibrium. We have to keep the system. We have first to achieve the translation equilibrium. The ring or the plastic glass should be at the center of this force table. Then we will adjust the pulleys. The pulleys are frictionless. We are using threads, and the threads are passing over the pulleys. And then we have mass hangers that are used to hold the masses. So we will be demonstrating in the in our experimental part. So this was about the experiment number 2. So you have to repeat this experiment for same masses. Let's say this is 10 grams, 10 grams, 10 grams with including the mass of the hanger. Then you will repeat it for, you will have to use more masses. Let's say 30 grams, 30 grams and 30 grams. Then in the third case, you will be using different masses. Let's say this is 15, this is 20, this is 25, but you will be using different masses. And when you will use different masses, then definitely you will have to adjust the pulleys accordingly. So always keep the first pulley at 0 degree for the sake of simplicity. You can use it anywhere, but for the sake of simplicity, keep the first pulley at 0 degree and keep the second pulley if you want to keep it at 120 degree or at 90 degree. So now let's discuss the graphical method. How to you will have a graph paper that we will be discussing in the experimental section. You will have a graph paper, right? So you will select a suitable scale. Let's say to select a suitable scale accordingly. So if my force is, let's say, 0.09 Newton, so I will select a suitable scale. You can select any of the scale accordingly. Let's say I'm assuming that this is 0.01 Newton. My 0.01 Newton is equal to 0.5 centimeter. So it means that from here 1 Newton will be equal to 0.5 dividing both sides by 0.01 centimeter. So if you divide 0.5 divide by 0.01, you will get 50 centimeter. It means that my 1 Newton is equal to 50 centimeter. So this implies that if 1 Newton is 50 centimeter, it means 0.09 Newton will be equal to 0.09 into 50 centimeter. So it will give 0.09 into 50 will give you 4.5 centimeter. 0.09 Newton will give you 4.5 centimeter. So it means that this 0.09 Newton, you will use a scale, a metric rule or a scale, and you will select, let's say this is 4.5 centimeter. So draw a 4.5 centimeter vector, and this is representing your 0.09 Newton, because this is equal to 4.5 centimeter. You have to Draw it on a graph paper. Select 4.5 centimeter. Draw a line, then draw an arrowhead. And you will have, and you should also know the direction. How to find the direction? You will be using a protector. So if this is the protector, this is 180 degree, this is, let's say, 0 degree, this is 90 degree. So you will keep the protector, let's say this is our graph. So let's say this is F1. F1 is, let's say, theta 1 is equal to 0 degree. So this is our F1, and F1 is, let's say, the length of this F1 is 4.5 centimeter. So you will draw a 4.5 centimeter line, and then you will put an arrowhead, and theta 1 is here 0 degree. So it is parallel to x-axis because it is 0 degree. So this is 4.5 centimeter. Now you will, let's say, our second force is also 0.09 Newton, but the angle is 120 degree. So exactly you will draw, then you will keep the protector here, and then you, let's say, 120 degrees here, then you will place a dot here in the direction of 120 degree, and then you will draw a vector of length exactly 4.5 centimeter. So this will be your F2, because F1 and F2 have the same magnitudes, let's say, in the first case. So F1 is 4.5 centimeter with theta 1 is equal to 0 degrees. F2 is also equal to 4.5 centimeter, but with 120 degrees this way. So the resultant will be here, right? This is the resultant. So let me draw a clean figure. So let me draw a more clearer view of this. Let's say this is our F1 on the graph paper. This is, let's say, our F2 at 120 degrees, and you are now, hopefully you know how to select a suitable scale. So you can even use, if you are not using this way, you can use, let's say, 0.1 Newton can be equal to 1 centimeter. It depends. What is your value? What is your value of the force? Then you will be using this one. Maybe you are using this one. Maybe you are using some other scale. It depends. So the magnitude of the resultant of this these two forces will be here. F R. This is the resultant, right? Now we know that the parallelogram law of addition. So if these two forces are equal in magnitude, so they must have an equal magnitude. So this is F1. Now I am adding F1 with F2. So now the parallelogram law says that if A plus B, if there are two vectors, A plus B, give us the resultant R. Then if I first add the first vector and the second vector and then the first vector, like B plus A, then this is actually commutative law of vector addition. This is the parallelogram law of vector addition. It means that if you are using A plus B and it gives you a resultant, and then you are using B plus A and it gives you the resultant, they will both give you the same resultant vector. It means F1 plus F2. Let's say if you are using this way, this is your F1 and this is your F2. So it will give you this resultant vector. But now if you are using the first vector as F2, now if you are using the first one F2 and then you are using F1, you will get the same resultant vector. F1 and F1 are parallel, F2 and F2 are parallel. This is your theta R, right? And here we will have a equilibrium force, F theta E. So this is making a parallelogram. It means that if you add F1 and F2, it will give you the resultant. And if you are if you are first adding F2 with F1, so it will again give you the same resultant vector. It will again give you the same resultant vector. So this is actually the vector law of addition. This is known as the parallelogram law of addition, vector law of addition. So vector holds commutative law of vector addition. Vectors have the property to hold commutative law of vector addition. So this was all about our today's experiment, translational equilibrium, and the purpose was to find the forces, the resultant of the forces, the equilibrium, and then to find a force that balances the two forces. So hopefully when we will be demonstrating this practically, then you will have a better idea how to resolve these forces. So this was the I know this is a very lengthy lecture on this translation equilibrium, but if you will have an idea of how these forces are resolved and how to use them in your calculations, it will definitely help you when you will be demonstrating. So this was enough for our today's experiment, the theory and calculations part. This was our experiment number 2, and in the next section we will be demonstrating this on our workstation. Thank you.